We're going to recap a bit of vectors today. So you may remember vectors is chapter 5 and 6. It is a big, fat unit, but there are some pretty basic skills in it, and then the complexity escalates, doesn't it? So we're going to start off with some pretty basic stuff, and then we'll get a bit more complex as we're moving along. So I've just got up here to begin with. Look at what I'm covering in one sort of go. We've got 5A all the way through to 5G, and I'm covering that in question 1 here. All of those concepts will be covered in question 1. So this is a pretty basic question with some pretty basic sort of skills that we're going to match together here. So we have 3 points in space, A, B, and C, and the first thing we're asked to do is find the vector AB. And all that means is the direction from point A to point B. What's the direction you would need to head in? And so the way we do that is we do the coordinates of B, so -2 take 3, -5, 0 take 1, -1, 1 take 4, -3. That's how we obtain vector AB. We can do the same for vector AC. Alright, so that's part A complete. Part B. Part B asks us to find -AC plus AB. So what we could do is we could put a negative in here, alright, a negative out the front and distribute it. That would give us the vector -AC, and then add it to vector AB. And what this is going to be, I wanted to write it like this, just to remind you guys of some of those relationships, right? -AC we can write as CA, alright? If we flip those letters around, it changes it from a negative to a positive, okay? So it's just going in the opposite direction, but it has the same, it's parallel, opposite direction but parallel. And then plus vector AB. And then we also remember, if these two letters are the same, all right, then we can blend it together to be vector CB. So that could be one way of thinking. So you've got 2 ways of solving this. You can put the negative there and add it to this one, or we can do this and find vector CB. So let's go ahead and do that like I've done. So vector CB, the vector from C to B, is going to be the coordinates of B, take the coordinates of C. So we're going to have -2 take 1, we're going to have 0 take 4, and we'll have 1 take 2. Vector CB. Excellent. So we've done part A, we've done part B. We've got part C here. Find 2 times vector AB. So if here's vector AB, then 2 times vector AB, we're just going to distribute the 2 into the vector. So it's going to be -10, -2, and -6. It's the same vector, just twice as long. Alright, doubles the magnitude. Okay, next we have dot product. We've got find vector AB dot vector AC. Alright, vector AB dot vector AC. So we're doing the dot product of these 2 vectors. So I'm going to write them out next to each other. So that's -5, -1, -3, and then we're dotting -2, 3, and -2. And so what we do is we do the x times the x, plus the y times the y, plus the z times the z. And we'll just evaluate that. 10, take 3, plus 6, 13. Okay, then we have the angle between 2 vectors. So this is just a formula for us. We have the angle between 2 vectors, cos of theta. Theta is the angle between them, is A dot B on modulus A modulus B. Alright, so if we want to find the angle between AB and AC, you can think of it like this. 3 points in space, A, B, C. We're finding this angle here, right? That's the angle between vector AB and vector AC. So we've already got the dot product of vector AB dot vector AC. Alright, so we already know that that part's 13. So we've got 13 at the top. Then we just need the moduli of each respective vector at the bottom. So the modulus of vector AB, alright, we get to recap modulus here. I might write it alongside of it. That's going to be the square root of 5 squared plus 1 squared plus 3 squared. So what's that? 25 34, 35. Alright, so that's root 35 for AB. And for AC, 2 squared plus 3 squared plus 2 squared. 4, 8, and 17. Alright, and just like when you're putting it in your calculator, just to make things simpler, you can write it like this, right? You can include it all in the same root, because root A times root B is equal to root of AB. And then we can just evaluate that using inverse cos. Alright? We'll move on then. So that's question 1, and that's a pretty solid recap of 5A through to 5G. So that's a big chunk of the content that we've explored. So then in 5H, we've got a vector proofs question. This is one we've seen before. I pulled this out of the notes book. It's an old exam question. It's a good one. So I'll just give it a quick sketch up here first. Okay. Now with vector proofs, right, there wasn't heaps of questions in the textbook, right? There's about 5 questions in the textbook. And you may remember I supplemented it with like a number of other questions. We had about 3 worksheets to work through, so we did spend a while on vector proofs. So they're a pretty important component. All right, so let's get into the question. We've got, consider the triangle OAB in which OA, so from O to A, that's equal to A. And OB is equal to B. All right. Points X and Y lie on OA and AB respectively, such that OX is equal to 4 times XA. OX is equal to 4 times XA. So this is 4 times longer than this. So it's in a ratio of 4 to 1, 4 parts to 1 part, right? And the same with BY. BY is equal to 4 times YA. So this is 4 parts and this is 1 part also. All right, in terms of A and B, find vector AB. So the vector from A to B. If we want to go from here to here, we're going to need to do AO plus OB is going to equal vector AB. That's what we're trying to find, right? We're trying to find vector AB. Now, vector AO is negative A. Alright, so it's A that got in the opposite direction. And vector OB is positive B. Alright, so this is a 1-mark question, but I've just made a bit of an elongated argument there. B, take that. Okay, now find vector OX. Alright, vector OX. Well, OA, alright, is A. OA equals A. And OX, vector OX, equals 4/5 of vector OA. Right? It's 4 parts out of a total of 5 parts. So that means OX is equal to 4/5 of A. Okay, use vector proof to show that XY is parallel to OB. XY. So we need to find XY in terms of A and B, and what we're going to see is it's going to be some linear factor multiple of B. All right. If they're parallel, they have the same direction. That has direction B, so this is going to be some linear multiple of B. So let's check it out. We need to find vector XY. So if we want to know the vector from X to Y, all right, that's going to be vector XA plus AY. Right? XA plus AY. And we know vector XA, the vector from X to A. Let's make these arguments separately, and then I think we'll bring them back together. We know vector XA is 1/5 of A. Alright, the vector from there to there, that's 1 part out of 5 of the vector A. Alright, and what else have we found? We know that vector, we've got vector AB. Vector AB equals B take A. Alright, I'm just going to restate that. Vector AB equals B take, lowercase b take A. And we need vector AY. And vector AY, the vector from A to Y, is 1/5 of the vector AB. So I'm just making the argument here nice and clear. Vector AY is 1/5 of vector AB. Alright, so in terms of A and B, that's 1/5 of B take A. So 1 on 5B, take 1 on 5A. Okay, we've got the components. We've got XA and we've got vector AY. Let's bring them together. Alright, we'll bring them together, so I'll make the argument. I think I'll make it just beneath it. I'll just make that a little bit lower. So what do we have? XA is 1/5 of A. Alright, so we want vector XY, and we've got vector XA is 1/5 of A, and we've got vector AY, that's what this argument was here. Vector AY is 1 on 5B, take 1 on 5A, those parts cancel, and we have 1 on 5B. Alright, so we've done it mathematically, but we should communicate it somehow. We'll just say something like, because, what are we going to say? XY equals 1 on 5 times OB, therefore XY is parallel to OB. Alright, because they're in the same direction, they are parallel. Okay, any questions about that one? Alright. Use the vector proof. Okay, part C. So now we're skipping a bit ahead to chapter 6, where we've got A cross B is equal to 4. Find the area of triangle OAB. So what we should remember then, I'll come up here. The area of a triangle is half A cross B. Alright, so and let me sketch what I mean on triangle. Okay? If this is a triangle, this is A, this is B, then the area of a triangle is half the modulus of A cross B. Alright, now we're told the modulus of A cross B is 4, so therefore the area of triangle AOB is half of 4, which is 2. Alright, so triangle OAB, not AOB. Same triangle, different way of notating it. Okay, then we have triangle XAY. Well, what we have in triangle XAY, right? Triangle XAY, if we were to do the area of it, it's going to be half, alright? And triangle XAY is this little part here, isn't it? Where this is 1/5 of B, and this is 1/5 of A. Alright? So it's going to be half 1/5 of A cross 1/5 of B. 1/5 of A cross 1/5 of B. Alright. What's common there? 1 on 5. Well, if we factorise it, we're going to have half 1 on 5, and then brackets, modulus of A cross B. Okay. What is the modulus of 1 on 5? 1 on 5. So we get half times 1 on 5. A cross B. A cross B we know is 4. So we've got 1 on 10 times 4. We've got 4 on 10. We've got 1 on 5. 4 on 10. 1 on 2 on 5 units squared. Alright. So we just have to make an argument there using the information that we've done. We didn't have any coordinates, did we? So we couldn't have made an argument using the coordinates. All right. I think we've got time for the next one. Are there any questions about the vector proof? All right. So they pop up every now and then. Let's move on to the next one then. So what have we included in the next one? We've got cross product. We're doing some area. We're talking about lines. It's good. Parametric equations are reasonably fresh. So this question that we'll work through, there might be one component of it that we need to touch on. but I think we can get through this question. We have a sailboat moves with this equation where distances are in meters and time is in seconds. And we've got when is it closest to a buoy located at -5, 2. Alright, so we can sketch the path a little bit, I suppose, because that might help. So if we've got it starting at x is 1, y is 4, sort of here, and it's moving in the direction -3, 1. So it's going to the left 3 and up 1. To the left 3 and up 1. So that's the direction it's moving. And we have a buoy located at x is -5 and y is 2. So that's going to be here. So -5, 2. That's the buoy. Alright, and here we have x, here we have y, and the parameter t is the time that's elapsed for this sailboat travelling from this position. Okay, so it's going to be closest, right? A point is closest to a line when they're going to be perpendicular. When they are perpendicular to one another. So let's call this coordinate B for the buoy, which is -5, 2. And we've got the coordinate of the sailboat. Alright, here's how they've described this equation. 1, 4 plus t times the direction vector -3, 1. And so then the coordinate for any value of t is going to be, I'm going to describe it like this: 1 take 3t, and 4 plus t. Alright, so the x coordinate is 1 take 3t for time in seconds, and the y coordinate is 4 plus t for time in seconds. So that's its coordinate. We've got its direction vector. The direction vector that it's heading in is -3, 1. So we want to know, when is this direction vector perpendicular to the direction vector of PB? Remember, this is P and it's travelling. So we need to find vector PB. That's the vector that the sailboat makes with the buoy. And we're going to go, when is vector PB perpendicular to the direction vector of the sailboat? And they're perpendicular when the dot product is 0, right? So let's go, I'm going to find it and then I'll re-explain my thought process behind it. So vector PB, the vector from the sailboat to the buoy. Here's the coordinates of P, here's the coordinates of B. We're going to do B take away P. What do we get? We're going to get -5 take 1 take 3t. Oh, right away. And we've got 2 take away 4 plus t. Right, don't forget brackets so the negative can distribute there. What have we got here? Minus 6 and plus 3t. And we'll have 2 minus 2 take t. Alright, so that is vector PB. Now we want to know this is the argument we'll make, closest when PB dot and the direction vector the sailboat is going in, -3, 1, equals 0. That's when they're closest. They're closest when they're perpendicular. Just grab it a moment. That's going to be, and then we're just mashing that. -6 plus 3t, take 2, take t, dot, -3, 1. Alright, so we're going to have -6 plus 3t times -3. And then added to 1 times -2 take t. And we need that to equal 0. So here we're going to get positive 18 take 9t. And then here we'll get take 2 take t equals 0. What are we going to get? We're going to get 16 take 8t. We get 8t equals 16, t equals 2. Nicely done.
Take 10, take.
Yeah, isn't that take? 18 take 2. Oh, minus, yeah, good. I was going to say, it works out a bit too neat for one that I just made numbers up for. Good, so what do we got there? 10. And then we've got t is 16 on 10, 1.6. Alright, so they're closest when time is 1.6. So it just says when is the sailboat closest to the buoy. So if you wanted to know what is the location of the sailboat, you take that time value and you put it in here, right? This is the position for the sailboat. We're good at this because we did this with our mosquito folder, so that's all fine. You can think of it, you know, the mosquito is one of the closest together. All right, part B, how fast is the sailboat traveling? Well, this is the direction vector, right? That's how far it moves in 1 second. And so the velocity, the speed at which it's traveling is just the modulus of that. The speed, I should say. The velocity is that direction, all right? But the speed is going to be the modulus of it. So when it says how fast, that means what's its speed. It doesn't make the argument though. We're going to say here's its velocity, minus 3(1). So it's going to the left 3 meters and up 1 meter for every period of time, every second. And so its speed is the square root of 3 squared plus 1 squared root of 10 meters per second. So just over 3. All right, let's make a link and then we'll run down to our assembly. Because I've done this on purpose, I wanted to make a link between a Cartesian form and a vector form of the equation of a line. We have the equator, so I was travelling somewhere around the centre of the globe, around the equator, and we've got the equator has the line y equals minus x take 10. When does the sailboat cross the equator? Okay, that's the first part. For what value of time does it cross? And what angle does it make with it? All right, so there's 2 components to this. So for us to figure out when it crosses the equator, we're going to need to equate the vector lines, right? We're going to need to make this into a vector line and equate them to figure out the time value. So for this vector, right, for this equator, obviously one point that it passes through is x is 0, y is minus 10. Okay, that's a coordinate that it passes through. You could choose any coordinate, okay? We just need some initial coordinate because the line of the equator is not dependent on time. It's not describing a position, is it? It's just describing a line traveling across a space. So we've got 0 minus 10 is its initial point. It could be anywhere, right? And then we have plus some parameter. We can't use t because its position is not dependent upon time. Doesn't matter what we use, s or lambda, so it doesn't apply. All right, what's the direction vector? Has a slope of minus 1, which means as x goes across 1, y goes down 1. So its direction vector, 1 minus 1. All right. Okay, so I better wrap this up. So to find the angle, all right, to find the angle between 2 vectors, right, that's a dot b on modulus a modulus b. Okay, here's the direction vector of the equator. Here's the direction vector of the sailboat. They're the 2 vectors you would use in this equation. That's how we find the angle. But the other part's a little bit more complex. When does the sailboat cross the equator? We've got to equate these 2 components, right? So we're going to have 0 plus lambda and minus 10 take lambda. So that's the line on the equator with regards to lambda, and we're going to equate them. So we have lambda equals 1 take 3t, and we have 10 take minus 10 take lambda equals 4 plus t. All right, we'll go ahead and solve here. We've already isolated lambda here, so I'm just going to shove that in there. Okay, simultaneous equations, bring them together to find the value for t for which it's true. So here I've got minus 10 take 1 take 3t equals 4 plus t. So what have we got? Minus 10 take 1 plus 3t 4 plus t. Let's have minus 11, moves it over. So we get plus 11, we get 15, and we get 2t, we get t is 7.5. Alright, so we've found the value for time when it crosses the equator, and we can find its position accordingly. Alright, so that's question 3 done. So then tomorrow when we resume, we'll move on from question 4. Roll of action. Alright, so let's proceed with vectors. So we got up to question 4, is that correct? Excellent, so we're looking at these 2 lines in space. We have line 1, and we're given the vector equation of it, and then we have line 2. And all we're given for line 2 is 2 coordinates. So we need to find the line that goes through those 2 coordinates. So for a line, we need two things. We need the direction, and then we need one set of coordinates. So in order to find the vector between these 2 points, so the first one is 4, 6, 0, right? And the second one is -3, -1, and +2. And if we want to find the line between them, we're going to do first the direction vector. So we're going to know what's the direction of this vector. So it doesn't matter what order we do it in, but I'm going to go here, -3 take 4, so it's going to have direction -7, -1 take 6, -7, and 2 take 0, 2. Alright, so that's going to be the direction vector of our line, and then it passes through either of these coordinates. So if we want to express it as an equation, right, we're going to say line 2 passes through, let's just say the first coordinate, 4, 6, 0, and then plus some parameter. We won't use the same parameter, but we'll use a different one. Let's go for lambda multiplied by its direction. This is its direction. Alright, so we figured out the direction. It passes through this point, and then it's going plus the parameter multiplied by that direction. And remember, you could use any point that exists on the line, because both of them do. It doesn't matter which one you use. So we have the equation of line 2, and we have the equation of line 1. I'm going to write that up underneath it, which is 3, 0, 2, and then plus the parameter is t, multiplied by the direction 4, 7, 3. Okay, so it says find the relationship between the lines. So let's think about lines in three-dimensional space. There's a couple of options, right? They could be the same line, all right? They could be the same line, or they'll be parallel, all right? If they're the same line, or if they're parallel, then they're going to have the same direction vector. So we can look and say, do they have the same direction vector, or a scalar multiple? And we can see quite clearly, you can't multiply that by a number to get this vector here. So we can say straight away, they're not parallel, which means they're not the same line. Okay, they're not going in the same direction. So that leaves us with two options. Either they intersect, they cross one another, or they're skewed, where they don't cross one another. All right, so for them to intersect, they have a consistent solution. That's the word, isn't it? A consistent solution. So we need to determine the values for lambda and t for which they intersect and assess whether it's a consistent solution or not. So they're going to intersect, for instance, when the x coordinates are equal. So that's when 4 take 7 lambda, okay, 4 take 7 lambda equals 3 plus 14. That's our first equation. They're also going to intersect when the y ones are equal. So we're going to go 6 take 7 lambda is equal to, and then we'll have just 17. And the last one is when 2 lambda is equal to 2 plus 3t. Now what I mean by a consistent solution is you can obtain a solution from just equations 1 and 2. Okay? We can rearrange that, solve it, put it in our calculator. But for it to be consistent, it's also going to satisfy this equation, the third one. So we obtain these values of lambda and t, and then we would substitute them in to determine whether it's a consistent solution. Okay? If it's a consistent solution, then they intersect, and we can find the corresponding coordinate. If it's an inconsistent solution, then they don't intersect and they are skewed. All right. Now I'm not going to go ahead and do that because I've just made up these things, so I'll probably get some nasty values of t and lambda, and it'll take a long time. But that's how you would do it. Okay. You solve these two equations. You plug the values you get in here to see if it satisfies it. All right. Is that okay? People happy with that? Excellent. All right, so that's question 4. So then let's move on to question 5. Question 5, we're looking at planes, we've got angles in space, we've got system of 3x3 linear system, so like 3 planes intersecting with one another, it's 46k. So part A, find the equation of a plane that is composed of line 1 and line 2. So a plane, right? A plane has this equation, ax plus by plus cz equals d. where A, B, C is the direction vector of the normal to the plane. How do you find the normal to the plane? It's the cross product of the direction vector of the two lines that compose the plane. So if you think we've got two lines here, line 1, line 2, and they exist on the same plane, right, the same sheet of paper, we want to find the normal vector. We'll call that n. The normal vector is equal to the cross product of the direction vectors, right? The normal vector is equal to the cross product of the direction vectors. So that means if we're going to do the cross product, we can set it up like this to do it manually, I, J, K, and it doesn't matter what order we do it in. It's just going to give us either a positive or negative direction, it doesn't matter. So the direction vector of line 2 is this one, -7, -7, and positive 2. And the direction vector of line 1 is 4, 7, 3. Alright, so I'll refresh how we do cross product manually. Alright, so what we do is we do I, and we cover up I, and then we do discriminant value. -7 times 3, so -21, and then it's going to be take away 7 times 2, take away 14. We have -21 take 14, lots of I. Okay, and then we do take J. Okay? The middle one, we're subtracting it away. We cover up J, and we do AD again, so -7 times 3. We're going to have -21, and then we have take away positive 8. And then we have plus K. Alright, we cover up K. We're going to have -49. Take away. And then we're going to have -4 7s 28, -28. Okay, and then it's just a matter of putting. That's how we do it manually. Remember, we can do it on our calculator as well. It's probably faster on your calculator. It's probably about the same, really. I think the advantage of doing it on your calculator is you're less likely to make a mistake. Because there's a fair few buttons you need to press on your calculator to bring it up. Alright, so anyway, I've evaluated this. I got -35I plus 29J, take 21K. Alright, so that's the direction vector of the normal. Alright, so we've got A is -35, we've got B is positive 29, and we've got C, which is negative 21. And if you can pull a factor out and get rid of a common factor, you can simplify that, right? Because it's just a direction vector. But we can't because of that prime number there. So, here we've got the direction. Let's plug it in. So we're going to have -35, alright? And then when we multiply it by, we need some coordinate that it passes through. It could be any coordinate, right? We know that this coordinate exists on the plane, and we know that this coordinate does as well. Doesn't really matter. Let's go that one because, I mean, they've both got 0 in it, but let's go that one. Going through the point 3, 0, 2. So we're going to go -35 times 3, and then we're going to have plus 29 times 0, and then we're going to have to take 21 times 2. And that's going to equal our D value, right? A times X plus B times Y plus C times Z equals D. We're going to solve this for D. It's 21 times 2. And do I go ahead and do that? I got -189 when I did it before. So -189. So therefore the equation of this plane, right, let's write it out, is going to be -35x plus 29y, take 21z, equals -189.
It's definitely not.
It's definitely not.
Wouldn't be. I got 147.
147, positive,
Negative.
negative. Should be the same regardless of the coordinate you put in, but
3 times 35 is 105 plus 42.
105. I've got 21 times 4 for some reason, not 21 times 2. I must have mixed up the coordinate. So 147. Thank you. Alright. So that's the equation of our plane, which is good we've got it because we're going to use it for the next one. That's where I got 4 from. I put that coordinate in. Find the shortest distance from this point to the plane. So, we've got a plane, and we've got some point in space, and we want to know the shortest distance from the point to the plane is when they're going to be perpendicular. Now, we derived the formula for this in the exercise, but in the exam you're just expected to use the formula. You don't need to derive it or perform some elongated process to arrive at it. So the formula is, it's the magnitude of A x naught B y naught plus C z naught plus D divided by, let's get a fresh one there, divided by the square root of A squared plus B squared plus C squared. Alright, so I'm just going to write it out rather than evaluating it because it is a big long thing again because I can make these numbers up. So we're going to have D equals, it's going to be the modulus of, so we're just going to make it positive, A, so minus 35, times the x value of the coordinate. What's the coordinate we're interested in? 304, so minus 35 times 3, and then we have plus 29 times 0, and then we have take 21 times 4. Here's 189. Alright, and all that's on top of square root 35 squared plus 29 squared plus 21 squared. Alright, so if you evaluate that, that's going to be the distance between the coordinate and the plane, the shortest distance.
Do you not add D? Is D in the numerator?
Yeah, good one. So D value is 147, so up here we have plus 147. Alright, plus because we're moving it over, and when we move it over, we're adding 147 to both sides. Yep. That'll be all the details there for number 5. Alright, number 6. So in number 6, we've got 3 planes in space, and we want to determine the relationship between them. So we have to make our way through the list, right? So first let's make it as a, what do we call it, an augmented matrix. So we're going to have 1, minus 3, minus 2, minus 9. We've got 2, 5, 1, and 3. We've got minus 3, 6, 2, and 8. Alright, so there it is as an augmented matrix. And let's try and reduce it to, what do we call it? Row echelon form. Right, so we're trying to get zeros here, here, and here. We're trying to get zeros in those positions so that we can see if there is a unique solution or see what kind of solution there is. Now the first thing we can do, looking at this, is none of these equations are a scalar multiple of each other, which means they're not parallel, they're not coincident. Okay, so none of them are a scalar multiple of one another. Excellent. So let's get to the process of eliminating. Firstly, let's try to get a 0 here. So if we do something like 3 lots of row 1 plus row 3. Sorry, how do we write that? We're going to write replace row 3 with 3 lots of row 1 plus row 3. Alright, that's going to give us 3 plus minus 3. Okay, so we restate the matrix with that form. So 0, here we have minus 9 plus 6, negative 3. We'll have minus 6 plus 2. We'll have positive 4, negative 4. And then we're going to have minus 27 plus 8, and minus 19. Alright, and remember there is a way we can do these in our calculator, but again it is quite clunky. But there is also a way you can put this in and get it to reduce it to row echelon form for you as well. So you can go straight from there to the answer using your calculator. But when these questions pop up in exams, they do want to see the row operations that we perform. Alright, so there we are. So now we've got a 0 here. Before we can get a 0 there, we need to make this one a 0 as well, so that we don't have some error occurring there. So we're going to replace row 2 with 2 lots of row 1, take row 2. Let's restate what we've got once we process that. 2 take 2, minus 6 take 5, minus 4 take 1, and we'll have minus 18 take 3, minus 21, we've got 0, minus 3, and minus 4, minus 19. So then we're looking here and we need to get a 0 here, right? Or it doesn't really matter where we get the 0. We're going to have a unique solution. We can do the 0 here, but we need zeros at the bottom, right? So what's going to be easiest? We're going to have to multiply by 5 and 4, or multiply by 11 and 3. And yeah, mate, we'll just do the 11 and 3 so we can keep it looking neat, I reckon. So let's replace row 3 with, and we're going to do 3 lots of row 2, take away 11 lots of row 3. 3 lots of row 2, take away 11 lots of row 3. So this is where you can make a mistake because we're doing 2 multiples, right? So that can be a little bit. So the first row stays the same, the second row stays the same. So we can just chuck them up. Minus 2, and we've got minus 9. Then we've got 0, minus 11, minus 5, and minus 21. Alright, here we're going to have a 0. And here we are going to have a 0 because we've set that up to be a 0. We're going to have minus, what's that? Minus 33, take minus 33, so they'll cancel. Then we're going to have minus 15, and maybe I'll write it out just so. We've got minus 5, 3 times minus 5, take away, and then we're going to have, what's that, 11 times 4. Alright, so we've got minus 15 plus 44, we've got 29. Alright, so that's 29. And then we have, this is the nasty one, 3 times minus 21, take away 11 times minus 9.
It's 146.
Thank you. Cool. So we've reduced it, and now we can determine the z value, right? So here we've got a unique solution. Why? Because we can obtain a z coordinate here, we can obtain an x, a y coordinate, given the z coordinate, and then we can obtain a z coordinate. So because we have a unique solution, because we've been able to reduce it like this with all those numbers there, it meets at one point. The 3 planes correspond, meet together at 1 point. Alright, should we find the solution, or are people okay with how to do it? Yes, we should find it, or no, you're okay? Right. Cool, alright, so that's vectors. Any questions about what we've performed with vectors? Cool, we'll stop there and we'll do integration when we get back from recess already.